project between biomedical engineering and the mechanical engineering department. In the interest of not stealing the thunder, I will again let the team introduce themselves to the project. All you.
Good morning, ladies and gentlemen. We're the ACL Protective Footwear Design Group. This is Jess, Mike, and I'm Nick. We're going to talk about today the background, our objective, the methods, the design methods, modeling, manufacturing, testing, and our final conclusions.
All right, just go a little bit background information how we came about with our project. What we really needed to do is do a lot of research about how the ACL tears were torn. Two major components into tearing the ACL is the hamstring muscle and the patellar ligament. Or the patellar tendon. You can see right up here in the diagram that when there's a high hamstring force, what will happen is that the hamstring will pull up on here. You'll get a high force on the patellar tendon, which acts on the tibia right here, causing an anterior tibial rotation. So that where the arrow is pointing actually shows that the tibia will rotate forward, causing a high strain on the ACL to tear. That's one of the main causes. How this happens is from an up and down jumping motion, which commonly tears the ACL. Another motion that tears the ACL is a side step motion, which you can see in the two bottom images of somebody demonstrating this. There's the what normally occurs is the valgus positioning of the knee, which causes the tear to occur. This happens with a high ground reaction force that occurs in the knee, creating the ACL to tear. What we're looking at with our project is where these actual ground reaction forces occur that cause the ACL to tear, where these actually happen in the shoe, and designing a mechanism to absorb these forces and prevent them from actually reaching the ACL. How our system works is we need to determine a time point and when our system is actually activated. So what we developed is two separate portions when the forces occur, which is the injury threshold, which is this line going over, and we have the high risk injury line, which is when the ACL tear actually occurs. In a normal shoe, you can see with this blue dotted line going up to the X, this is a normal shoe. So what happens is that either when you're doing the jumping or you're doing the sliding cut, there's going to be a high force and nothing preventing from the ground reaction force actually tearing the ACL. What our system actually does is the system is activated at the injury threshold point, absorbing the load that's going to happen on the ACL, preventing it from actually reaching the high risk injury point and preventing the ACL from actually tearing. So what we're looking at is preventing the ground reaction forces from reaching the ACL. Our other goals are to maintain the normal shoe function, so we don't want to interfere with how the player is performing. We want to apply it to an athletic shoe because that's the major application for the design. And we want it to be a reusable and recoverable system that will be able to be used step and step and again, and if the system's activated, it won't actually fail. For our design methodology, we used the axiomatic design principles, which broke the project into functional requirements and design parameters. With these, we created a collective, exhaustive, mutually exclusive system, which helped outline the design of our project to make sure there wasn't any interference in any components into the design that weren't needed. With this, we designed two separate systems, one with the compression, like I talked about before, that prevents the high forces from happening with the interior tibial rotation. This was theoretically based with some calculations that we played out with an air chamber system. So a high force is applied onto the air chamber. Once the air buildup reaches the pressure inside will reach that injury threshold, the pressure valve is released, allowing air to leave the system. When the air system leaves this chamber, it allows a greater motion for the heel to travel down, delaying the peak occurrence of the reaction or of the ACL forces from happening, and also allows for extra cushioning for the while the person's running. So the pressure relief valve will only be activated when the forces reach that injury threshold line that we determined, and then it would prevent it from reaching the high risk section. Then we also have, in order for it to keep a recoverable system, you have your intake one-way valve right here that allows the air to travel into the system after it's been activated, but doesn't allow the air to leave the system. Our major design of the project was also for our shearing mechanism. So when I talked about with the valgus positioning of the knee, we have a shear design going here that absorbs the shear forces. So what you have up here is a two-layer system and a cantilever beam positioned on the spot top here. What happens is that when you have the high forces of the shearing coming off with this arrows pointing, there's going to be a force applied to the cantilever beam absorbing the forces. With our design, we have a double beam system. The smaller beam preventing the shoe from moving under normal playing conditions when the player's not reaching the injury threshold. But when that first beam bends over, when it reaches above the injury threshold, a taller beam is then activated, allowing extra motion, allowing the shoe to move, allowing the shoe to shear, and absorbs the extra forces that would possibly tear an ACL.
So when we had our axiomatic breakdown complete, we could move on to constructing our prototype. To do that, first we created a solid model of our design, which you can see up here. All of these features in the design are all related to our design parameters and our axiomatic breakdown, which are then related back to functional requirements of what we want our mechanism to do. Because we were making our prototype out of rubber, we also had to create a mold modeled there in the bottom left. You can see the center part of the mold is just a negative of our prototype, and then on the base part we have holes we can use. The holes therefore is for sliding pieces that we'll use to contain the sides so that the material doesn't leak out, and then we'll bolt them together at the bottom. Over here in this corner you can see a finite element analysis of the beam design. We did that to check to make sure that the beams wouldn't break under the testing that we're going to implement. So once we had our mold modeled, we could import that model into CAM software and then design and calculate the tool paths we would use to machine. Once we had the tool paths, we machined the aluminum stock and created the mold you can see up here in this picture. You can see the bolts I mentioned earlier, the acrylic side pieces that we cut with a laser cutter. You can also see some of the caulking we used to contain all the material to make sure we were making a mess. Down here you can see our material being poured into the mold. And then finally over on the bottom you can see our final product.
Alright, once we had our design made up, we designed and developed a testing apparatus to use in a uniaxial tensile test in the Instron machine. We tested at 12,000 pounds per minute, and we got a load versus extension graph. Between the 0 and 3 extension is when both beams are being activated and absorbing the load. At 3 millimeters extension is when the smaller beams will fold over, contributing no load absorption to the system. So we have a nice steep line here, and then when we reach the injury threshold line, it will plateau off and, like our original hypothesis graph, absorb the load. We also tested in the Instron machine varying beam sizes, dimensions, and in that we determined that we could change the activation load, the plateau level, and the slope, meaning we can, based on the size of the person in the shoe, that we can control the beam to be very personable to each different person. And then we went and made the shoe. We put together and did it on a force plate. We ran on the force plate at about half speed, and when we touched the force plate, we came off at a 45-degree cut. The graph right here on the left and the right is the control without the beam system, and the one on the right is with the beams. The initial, right here, these peaks, is initial contact, and down at these is where we start pushing off, making the cutting motion. As you can see in this graph, the control is a very steep, steady, quick rising load to a very long peak load. And this graph in the beams, this is where she starts pushing off, and this slope is the same as this slope, which is what we want. This will be under the injury threshold. Once it reaches that injury threshold, down here you can start to see it starts to slide, and it's increasing the time that the load takes to get to the peak, which gives it a less peak load on the ACL.
Alright, so just to summarize the results and conclusions, the design of the beams that we actually did for this mold were designed for testing. In order to do the testing to get the data to see how the beams behave, we didn't use as strong a material that would work under the normal injury threshold that we would be. We made the beams activate at much lower levels, that way we can see the behavior, how the beams react, and to basically a proof of concept to prove that the beams would behave in the manner that we'd like. In a final design, we would look at a much stiffer system that would hold the system together under normal playing conditions, and then once the forces reach that injury threshold where it would be a actual dangerous level, then the system would activate and bend over. But for safety purposes and to design a proof of concept, the material was much less stiff, so we were able to actually get some valid results. For the compression system, right now, we designed that system very late in the project. Right, currently, we're looking at designing it, building it, and trying to test the air system. Right now, we have it proved that mathematically that we can withstand the forces of the compression system happening. There are pressure relief valves that will work under the forces that we're looking at, and we believe that the airflow with the system being recoverable, that we will be able to apply it to an actual design. As we just went over, our testing was successful. It proves that the beams do behave in the way that we wanted, that we can activate it at a certain level and see a change in the force absorption and the time it takes for it to reach the high forces. And we're able to create a working prototype that we were able to run it with the tests. The system didn't fail. We didn't have to go back and create the system after we ran our testing. The shoe sitting on the table right now is the actual shoe that we did our testing with. So we were able to have a working prototype, and our testing went exactly as planned. Any questions?
Sir?
Can you go back to the force plate graph, please? What does it look like without the device?
Without the devices that we grabbed
Oh, that
right
is
there.
the blue.
That's to
Yeah.
control it.
That's the
Okay.
control data. It's a same foot acting on the force plate, just not having any devices built in. So you can see the major changes where the arrows are pointing to. So you'll see a steep slope as it's coming up,
I see.
and then when you actually have the device activated, you'll see that change in slope and the delay in time that it takes to reach the forces.
Just one quick add-on question to this. How did you look at how this device affects the stability of other motion at all?
Well, right now, since it was designed to test the behavior of the beams, right now the system's really unstable. With a stiffer system, you would have less, it would be more stable, less ankle injuries, because that's really what we're concerned about right now with the design. But that's what the stiffer, the lower beams, because it's a double beam system, the lower ones are set there for stability purposes to maintain normal play. But then once the forces get high enough, those beams will bend over, activate the taller beams in the system, and then allow the motion to turn back to its normal state after the forces were applied.
Sir?
So the test subject in this case knew so you knew which one you were testing,
Yes,
which one you
yeah.
were biased.
It was, at first it was, because first we were doing I originally had both of the shoes, so we had the same exact shoe, we were doing a left foot and a right foot test. But we noticed a lot of varying results, one because I'm not as coordinated with, or not equal coordination with the same foot. So we reevaluated our testing that we were doing and decided to have the same foot. We didn't have the same shoe to use. So like the foot, the holding mechanism or where your foot actually goes into was slightly changed. So it might vary our results a little bit, but we were using the same foot, so it was much easier to repeat the data that we're looking at. But yeah, there was a little bit of bias because I did know the mechanism was going through, but it's hard to create a system that you don't.
So if you wear the shoe, you know you're wearing an experimental shoe versus a control.
Yeah, I didn't know that was going on.
And do you think that a naive test subject would?
In this design, yes, because the system's not as stiff as it should be. Theoretically, if we created a stiffer system, you shouldn't be able to tell unless the forces reach the higher force.
So what I'm thinking is just subconscious.
Yeah, that's,
I'm just thinking, if you get a guy from the track team,
mhm.
and you say, we're doing a test, use this shoe, use that shoe, there's no idea what you're doing. I think that would be interesting to see.
It would be, yeah, there's a
To
lot,
me, it would be.
yeah, there's a lot more paperwork with getting outside
understand.
people to test, but that was basically what we were going for.
You said many tests. I see one cycle each here. What's your N? And how much does it change the graph each time?
It was, the control was very repeatable. What we're doing, there was a slight varying, I believe in you guys, if I say anything wrong, correct me. The distance, the high peak force changed a little bit, and the actual time that it took the person to push off varied a little bit, but the graphs were very repeatable. With our actual test subject, the graphs were also very repeatable. There were just one or two results that weren't as accurate, but we did, I think it was 6 testings of each, 6 different successful run-throughs that we were able to get repeatable data.
Just can you quantify very repeatable?
Well, the graphs, when we overlaid them, they were very, very similar.
just saying, you know, someone might say that the control and the test there, if you overlay them, are very, very similar. You know.
Yeah, I mean, the behavior going in is similar to what we want to use. It's really the behavior of how, when you're pushing off, that's really important, because the force, the numbers in this situation aren't as important, because the system isn't designed right now to absorb the forces, because we need to get the behavior of the beam and make sure that the beam behaves in the pattern that we want. And then a more stiffer system would be designed to actually work in a injury situation.
You still should analyze the significance of your separate tests. But that's it.
So, I have a question, sorry. A lot of ACL injuries, in addition to being valgus hyperextension, are also posterior hyperextension of the knee joint, which is actuated either at the ankle or at the knee, as opposed to in the foot. So, you know, maybe you can help me understand how changing the foot mechanics is going to change my ankle mechanics, because it doesn't look like the ankle's constrained and it doesn't control my knee mechanics
No.
either.
What we looked like, because a lot of the ankle mechanics seem to go into it, but what we looked at was that the location of the ground reaction forces is really consistent in all of the different positions of the knee. So when you had the valgus knee position, we had the anterior tibial rotation, you had the high force concentrations in these specific areas. So that's what we noticed was consistent in our data, was where the ground reaction forces were located. So we noticed that there was a high force underneath the heel for the compression mechanism, so we want to center our air system underneath the heel for that absorption. For the shear mechanism, we noticed that there was a high force going in that direction, even with an incorrect ankle position. You still had that high ground reaction force. And you're not really able to reposition the ankle, because we were looking into a lot of that at the beginning of the project, was we want to absorb the force in the compression, absorb the force in the shear, and reposition the knee. And it's really difficult to reposition the knee